Section 22.2 talks about the alpha-bromination reaction. And this is a pretty simple, straightforward reaction. If you have a ketone and you treat this with bromine with H+ catalyst, you form a product that replaces a hydrogen with a halogen at the alpha carbon. The reaction proceeds, of course, through the enol. So what we have is a protonation. This is oftentimes done in H3O+, for example, so H2O is present. The first step, you have protonation of your ketone, the carbonyl oxygen, okay? And next, we want to deprotonate the alpha carbon, okay? The alpha carbon here. The only strong base we have in solution isn't going to be H+, it's not going to be bromine or even bromide. I'd probably use water. The reaction solvent is present in greater amount, so this is going to deprotonate. And I'll just show one set of arrows to give you the enol, okay? So that's deprotonation. Now recall again that the equilibrium between a ketone and an enol strongly favors the keto form or the keto tautomer. But if you have 0.1% of this enol present, that very rapidly reacts with bromine, okay? Bromine is a great electrophile, and the enol is a carbon-centered nucleophile. So we call this A for attack, and what you get here is a protonated, bromoacetone. The last step is to remove that hydrogen, and so water here will deprotonate that, giving you the neutral ketone or aldehyde from your starting material. Okay, so that's PDAD, PDAD, okay, is the sequence of steps to convert a ketone to the alpha chloroketone or alpha bromoketone, okay? If you take cyclohexanone and you treat this with chlorine, okay, with H3O+, all right, you'll get chlorocyclohexanone, okay? Now, one of the good things you can do with alpha-haloketones is treat this with pyridine to give you an alpha-beta unsaturated ketone, okay? So here's alpha-chlorocyclohexanone. We say alpha-chloro because the chloro group is attached to the alpha carbon, okay? And pyridine is base. Pyridine looks like this, okay? This is pyridine. We call this PYR in abbreviations. So if I write PYR like that, it means I'm adding pyridine and, warming it up or something. And this right here will give you an alpha-beta unsaturated ketone. What does that mean? It means the unsaturation is between the alpha carbons and the beta carbons. Remember, unsaturation means that you have a double bond or a triple bond between two carbons, okay, in this context. The way this mechanism works is simply E2. So there's the pyridine. It's going to grab this hydrogen, okay? Electrons are going to move in to form the carbon-carbon pi bond, and chlorine is your good leaving group, okay? Semi-good leaving group. Bromine would be better, but so here are a couple different reactions to remember, okay? Now, I want to talk about regiochemistry. Now remember, the word regiochemistry refers to where or what region of the molecule is going to react. So for example, we had reactions back in the first semester of organic chemistry where we added water and H plus to an alkene, and we discussed Markovnikov's rule, how the OH goes here, not there, okay? So we want to discuss this reaction here. Say we have methyl cyclohexanone, and we treat this with bromine, and let's do H3O plus once again. And you'll see that it's possible to replace the hydrogen on the right alpha carbon with a bromine, or it's possible to replace the left alpha hydrogens with a bromine. And so we could anticipate getting two possible products. Okay. Now, the major product turns out to be the one on the left. Okay. And this is because this comes from an enol that's more substituted from the vantage point of the enol. Okay, so here's the enol that would give you the product on the left, and let's draw the enol that would give you the product on the right. Okay, and this goes back to the concept of alkene stability. Remember that the more substituted alkenes are more stable. If you look at these two alkenes, the one on the left, of course, is more substituted because it has a methyl group, okay? It's got this carbon, right? And it's got the OH. Both of them have the OH. This alkene here only has one, two, okay, two carbons. It's got a hydrogen here, okay? So if that hydrogen were a methyl group, that would make the alkene more substituted, okay? Review alkene stability here. This would be back in chapter 6 or something of the textbook, all right? So if you have a molecule with a more substituted side, okay, this carbon is secondary, this carbon is primary, you're going to have a reaction at the more substituted carbon. So if we treat this with bromine and H3O plus, we're going to get 2-bromo-butan-2-one. I'm sorry, 3-bromo-butanone, okay, with the ketone at the 2 position, all right? So the bromine is going to go to the more substituted carbon. That's just an easy way to remember it, okay? Now, the next thing I want to talk about is the alpha bromination of carboxylic acids. This is called the Hell-Volhard-Zielinski reaction. Okay, 3 different chemists, and it takes carboxylic acid, okay, and it treats it with a number of different things. You add bromine, phosphorus tribromide, and then in step 2, we add H2O. And what we make from this is the alpha bromo carboxylic acid, okay? The textbook kind of sketches out the intermediates, how you form the enol type of looking thing and how it reacts. I'm not going to go over any of the mechanism here or show you how that works, just because I don't test my students on the mechanism for this, okay? It's kind of a very side topic. If you're taking a very advanced class, like graduate school, graduate class, they might ask you, so you would want to review that, okay? let's continue onwards. So let's do, before we jump into too much stuff, let's do some practice problems. Problem 11 looks pretty good. Okay, this problem is fairly simple. It asks us to predict the products, and you need to remember that this carbon right here is the alpha carbon. It does indeed have a hydrogen. Let's draw it in. And so what we want to do with these reagent conditions is replace that hydrogen with a bromine atom, okay? The molecule on the right, okay, here's the carbonyl carbon of the carboxylic acid, and here's the alpha carbon. We want to draw a hydrogen there to make sure that there's not a trick. If there is a hydrogen there, these reaction conditions will replace that hydrogen with a bromine atom. Okay, that's all you need to remember. Any one of these reactions would make great flashcards to try to memorize it. Let's do another practice problem. Problem 12 takes very little time messing around before they jump right into some really hard synthesis problems. Use the reagents that you would use, identify the reagents that you would use to accomplish each of the following transformations. You will need to know all of the reactions from all of the previous chapter, chapter 1 through 21, okay? So we want to identify and use retrosynthesis. That is absolutely necessary. So here we see that there's a bromine alpha to a carboxylic acid. So thinking backwards, that could come from a carboxylic acid. Okay. And then we want to bridge the gap. All right. We want to count carbons very carefully. Aside from the 6 carbons in the phenyl ring, we have 1 carbon outside that ring. And here we see that we have 1 carbon outside the ring here, and we have a new carbon that's a carboxylic acid. And we know that that can come from CO2 if we treat the halide with magnesium and then carbon dioxide, right? That will make the green yard, form the carboxylic acid, and it's kind of all downhill from there, okay? So one of the ways we could synthesize this is to take our benzyl bromide here, treat this with magnesium in diethyl ether, okay? Diethyl ether is the solvent that stabilizes green yard reagents, so we do want to include that below the arrow, and this will make our MgBr there, okay? And then there's a couple of steps here. You add CO2, okay? That would be dry ice, crushed up perhaps. And then you would add, acid, H3O+. And this will get us to our carboxylic acid. Okay, nice carboxylic acid having the 1 additional carbon atom. And that 1 additional carbon atom comes from the carbon of CO2. And then what we would want to do is perform this Helmholtz-Zielinski reaction. So remember again, it contains bromine, okay, phosphorus tribromide, okay, and then water, okay, and that's going to give us the target molecule. I'll just draw it out here. Okay, so it's key working backwards because that halogen is kind of confusing. Remove it and then think about carboxylic acids, which we learned about in chapter 21. Let's do part B. In part B, we have a similar situation. We have this halogen just hanging out there, and it's on the alpha carbon of a carboxylic acid. So we want to think backwards using what's called retrosynthesis, and we use these weird arrows. Think of them as time travel arrows, okay? You're going backwards in time, and you're playing like a YouTube video backwards, and it looks all goofy, okay? And so what we have is a carboxylic acid, okay? And now we have to look at the relationship with the starting material and try to bridge the gap, okay? Let's start counting carbon atoms. So there's this tert-butyl group here, 1, 2, 3, 4, 5, 6 carbons. And over here we have 1, 2, 3, 4, 5, 6 carbons. So we're not increasing the number of carbons. We are simply changing the functional group, an alcohol to a carboxylic acid. So I think you know already how to do that. So let's sketch in the answer here. If we take this and we treat this with a Jones reagent, okay, I just write Jones. I don't write sodium dichromate, sulfuric acid, H2O, acetone. I just write Jones to keep it simple for my students. This will make the carboxylic acid, okay? And then we can treat this with bromine, phosphorus tribromide, and step 2, water. This will install that halogen on the alpha carbon there, okay? The alpha carbon. And we're done. Let's do part C. All right, once again in part C, we have this halogen on the alpha carbon of the carboxylic acid. So using retrosynthesis, we think backwards, and we think that that could possibly come from a carboxylic acid with an alpha hydrogen there available for some reactions. And then we count the carbons to make sure we have the right connectivity and the right number. We have 3 carbons, and here we have 3 carbons, and at carbon 2 is where the functional group changes. So we can change a nitrile to a carboxylic acid using, okay, lots of acid and heat, okay? So H3O plus, or H plus and water and heat, okay? Very concentrated acid, okay? So I'll just write H plus, H2O. Don't forget to use the triangle there. Triangle means heat, okay? And that will get you to the carboxylic acid in 1 step. And, well, I don't know why I wrote 1 then. And then we treat this with bromine, okay? Phosphorus tribromide, that would be step 1. Step 2 would be water, and that will give us the target molecule. Let me draw it out. Okay, remember that a COOH group is a COOH group. Okay, we have an octet on both oxygens. And so that's how you do some synthesis problems. Okay, let's continue with the chapter here. Next, we want to talk about alpha-halogenation under basic conditions. So we've already talked about how you can take something like this, okay, and treat it, for example, with chlorine and acid, all right? And we pick on the more substituted alpha carbon and replace that group with a chlorine. And we know the reaction proceeds through an enol that's going to be more substituted when you have a choice. Okay? Now, it turns out you can do this same sort of reaction with sodium hydroxide. Okay? Sodium hydroxide and halogens will react let's do bromine and sodium hydroxide. Well, we usually put the NaOH up on top, the bromine down on the bottom. Anyways, these will give you this guy here. Now let me show you how the mechanism works. Okay, in the first step, you're going to have hydroxide, okay, deprotonating and giving you the enolate. Okay, that's in equilibrium. That's a deprotonation reaction, and we form the enolate. Okay, then bromine is the electrophile that gets attacked. Okay, so this enolate with its carbon-centered nucleophilicity is going to attack the bromine atom and directly give you the reaction product, okay? So you do need stoichiometric amounts of sodium hydroxide, and you do need stoichiometric amounts of bromine, so it's not really catalytic. And so that's attack. So the curved arrow reaction mechanisms are DA, deprotonation, and then attack. So it's only 2 steps for this one, okay? And that's basically what I wanted to talk about there. The book does talk about the chloroform reaction, but I'm not really interested in discussing those, okay? So that's it. That's it for this chapter. Thanks for watching, and please subscribe.